Hello, everyone. Am I audible?
Yes, sir.
Okay, thank you. Let me share my screen. Can you see my screen now?
Yes, sir, it's visible.
Okay, great. Thank you. Let me just move the unnecessary things around. Okay, so hello, everyone. So I have a question, like how many of you think that your passwords are secure? Okay, so it can be broken soon. Now, how? So hello, this is Navin Kumar Chhibber. I am a AI and data leader, and currently I'm handling data engineering and digital transformation project. And currently I am living in uh, Sunnyvale, California. And my topic is getting ready for the post-quantum security. So the purpose of this presentation is to make everyone aware about the that quantum computers can break existing security protocol using Shor and weaken the AES security by Grover's algorithm. Now, I just want to give a brief introduction about what is cryptography. So cryptography is the process of hiding and coding the information so that only the intended recipient can see and read it. Okay. So what it does, it leverages the hiding information using the transformation and mathematical difficulty to encrypt the information. Okay. Transformation readable like plain text, which is the original text, and into a unreadable text, which is called ciphertext, which is encrypted. So in the encryption process, what we do, we have a plain text, we add some key, then we pass that into some encryption algorithm, and finally we get the encrypted text, which is called ciphertext here. And in the decryption process, we do the reverse of it, of the process which we did earlier. In the encrypted text, we add the key, we pass that to the algorithm, and finally we get the plain text. Now we have two type of encryption. One is symmetric encryption, and the second one symmetric. In the symmetric, we use a single key for both encryption and decryption, which is one of the example of such encryption mechanism is AES. It is very fast because we are using only one key. And generally we use in encryption the data side, like the file, disk, backups, okay? And in the symmetric encryption, we use two sets of key. So the first is the public key and the second one is the private key. So such uh, algorithms are RSA and ECC. And we generally use this at the key exchange layer and the authentication layer. And as I mentioned here, ECC is very fast and uh, and more efficient with the smaller key than RSA. Now, what is the current process? So we have three layers of authentication. The first is key exchange layer. Second one is the authentication layer, and the third one is data encryption layer. The first is RSA. In the first layer, we use RSA. The second, for the authentication layer, we use ECC, and third layer use AES. Now, what is RSA? So RSA is it use public and the private key, and the second is it use mathematical difficulty of factoring the large number to encrypt any of the data. Okay, we use it as on the layer one key exchange layer. Second is ECC. It use difficulty of mathematical challenge, which is elliptical curve discrete logarithm to encrypt any data. And generally, we use this at layer two, which is called authentication layer. Now the third one is AES, which use sequential transformation, and in those transformation we hide the actual information. Okay, and we generally use this algorithm on layer 3, which is called data layer. Now the thing is, uh, quantum algorithms, which is a Shor algorithm and Glover algorithm, they are very fast in trying the different things. Okay, so a Glover algorithm can try different keys very fast. Okay, so it can use a different permutation and combination of passwords very fast, and it can break eventually. Okay, and Shor algorithm is very good in solving the difficult uh, prime numbers solution very fast. Okay, so Shor algorithm can do can resolve the uh, prime numbers prime numbers very fast, and your Grover can try different permutation and combinations of password very fast. Okay, so these are the two different capabilities of the quantum algorithms, which can break the passwords and it can encrypt any of the data. This is just a small summary of whatever I have told. Now, what's a threat is Shor algorithm, which as I told earlier, it can break RS and ECC by solving the underlying math problem. Because what it does, it can do, factoring the large number and solve the discrete logarithm very fast. Okay. Now, what is the workaround or how we can save our information? So what we do, because it is only having a perfection of solving the factoring the large number and the discrete algorithm problem solving, it can't do other problem solvings. Okay. So what we use, we add some other mathematical problem into the encryption methodology. Okay. And in Grover algorithm, it drastically reduces the effective time by key searches. As I told you, like it can try different permutation and combination of passwords very fast. Okay, and eventually it can break your password and it can encrypt your information. Okay, so how we can save it? So what we do generally, it does not, it can't break actually AES 256. Okay, because it has a larger keys. Okay, so this is the weakness of the Grover algorithm. So we utilize these weaknesses to save our data. Okay, now what's the impact and how we can protect it? So the impact would be on the secure communication. Okay, your blockchain systems, IoT and embedded systems, and cloud computing. On how we can protect this, as I explained earlier, we can add some different level of mathematical problem. Okay, and we can add some more level of complexity so that it would be more difficult for quantum algorithms to find the information. So we have tried uh, different algorithms: lattice-based cryptography, code-based cryptography, multivariate and hash-oriented cryptography here. So what lattice-based cryptography is, it add the high dimensional grid into the, in the hiding process, and it would be very difficult for Shor algorithm to find the information from that jungle of the, you can say, the complexity. In the code-based cryptography, we add new and hard math problems, and this is the way we save our information. In multivariate and hash oriented, we add new and hard math problems, okay, so that add, uh, we can save our information. So what is the proposed cryptography framework is? First is the quantum resilience. Provide protection against the attack, against an attacker with scalable quantum computer capabilities. It should be backward compatible. Ensure that it should be compatible with the classical algorithms like RSA, ECCES, and it should seamlessly work with the post-quantum cryptography algorithms as well. At the same time, it should use less CPU and less memory and less resources as well, like storage and communication. And what are the target environments we want to try? It should be on cloud, IoT, blockchain. This is a performance matrices. As I mentioned in the summary here, execution time, PQC algorithms, definitely these are slower than the classical. Security-wise, PQC is uh, more secure when we use with classical algorithms. Storage requirement, PQC has a larger keys. Resource requirement, CPU and memory, lattice-based Kyber and Delethim if are efficient, and hash-n is heavier. And scalability-wise, lattice-based Kyber and Delethim works well, and hash doesn't having a good performance. This is just a summary. So what is the proposed transition plan? This is a very important slide, guys. So you need to understand here, like we have a three levels. First is the key exchange layer, which is a top layer. The second layer is the authentication layer. Uh, and the third one is data encryption layer. So in the existing architecture, we use RSA algorithm for the key exchange, ECC in the authentication layer, and AES in the data encryption layer. So during the transition plan, what we propose is for the backward compatibility, let's use RSA, but with that, we should use lattice-based Kyber PQC, post-quantum computing algorithm. On the authentication layer, for the backward compatibility, we will use ECC, and for PQC, we will use lattice and hash algorithms. And in data encryption, we will use class AES with PQC lattice-based Kyber algorithm. But once we complete our transition, we can remove the RSA from the key exchange. We can just keep working with the lattice-based Kyber. In the authentication layer, we can remove ECC and we can just use lattice and hash algorithms. And in the data encryption, we have to use both AES with PQC. So the conclusion is quantum computing represents the significant challenge, as we discussed, uh, and how we can secure it. So we have to use PQC, post-quantum cryptography. It provides the viable defense framework, and despite some computational overhead. So performance would be definitely a little bit low, or it will degrade. But yeah, security-wise, it would be improved. Now, what's the strategy? We will use the hybrid approach initially, and later we will move directly to the we will remove the extra level of algorithms. Like from the first layer, we can remove RSA. From the second layer, we can remove ECC. But at the third layer, which is data encryption layer, we have to use both. Okay. And yeah, if you want to learn more about the complete mechanism which we have followed, you can find this paper. This is this is IEEE paper and quantum resistant cryptography models for next gen cybersecurity. This is my contact information. You can connect with me. This is my IEEE email address, my LinkedIn, and my ResearchGate profile. And this is my QR code for LinkedIn. Yeah, thank you. Let me know if you guys have any question.
So, as there are no questions at this moment, thank you for delivering an insightful session on one of the most important challenge facing the digital world. Your expertise has helped us better understand the future of cybersecurity and the preparation required for the post-quantum era. We are grateful for your inspiring contribution. Thank you so much, sir.
Thank you.